It's a great pleasure to introduce Christian. It was also a great pleasure to collaborate with him on many problems. He's now a postdoc at Utrecht University, and previously he was at TU Vienna. So obviously a conference like this is not fun without having a talk on how do you do heavy ion collisions in ADS-CFT. And I was thinking that whom to invite for such a talk. And immediately Christian came to my mind because he's one of the best numerical experts now in game, and he's one of the youngest also. And because the subject is also very young, I thought of inviting him to give this talk. And he's one of the really best in this particular field. So it will be a great fun and great privilege to hear your talk. So over to you now.
Okay, hi everyone. So first, thanks Ayan for this very kind and super nice introduction, and for having me at this very nice school and workshop. So the topic of my talk is numerical holography. And the idea is to give you some kind of introduction to how to describe and simulate the dynamics of strongly coupled systems using ADS-CFT with numerical GR methods. So these methods, they have many applications. As Ayan already mentioned, the method that I will present and talk about was actually developed to describe shockwave collisions in N=4 superhang Mills theory as toy models for heavy ion collisions. And there is a famous picture of, or it's one of these pictures of a shockwave collision in N=4 superhang Mills theory, which is based on a gravity calculation where you do a collision of gravitational shock waves in ADS-5. Other applications include more condensed matter-oriented questions like the formation of steady states in quantum critical systems. So this picture here shows you the time evolution of the energy density in a system which consists of two heat baths which are in thermal contact in an interface, and on this side the temperature is lower than on that side. And what you find when you do these simulations, that a so-called steady state forms on this interface, which is a region of constant energy density and constant energy flow from the warm side to the cold side. There are other interesting applications for the dynamics of vortices in superfluids and applications to turbulence. I will briefly talk about the shockwave collisions, and if there is enough time, I will also talk about the steady state formations, but I will not talk about these two topics. I just chose these pictures because they're, in my opinion at least, the most beautiful pictures that you can find in ADS-CFT numerics so far. Okay. Before I begin, there is a selection of useful references for this topic. There's, of course, Johanna's book on ADS-CFT is a perfect introduction to the topic. On the more applied side of ADS-CFT to heavy ion collisions is the book by Jorge Casaldera-Solana, Hong Liu, David Mateos, Rajagopal Wiedemann. And very important reference is, of course, the review article on characteristic methods for numerical holography by Chesler and Jaffe. And for the very efficient method, the very efficient numerical method to solve these the differential equations that you encounter in this kind of problems is the book by Boyd on spectral methods. So this is the outline of my talk. I split it into three parts. In the first one, I give a short introduction to ADS-CFT. Johanna already told you everything you need to know. I will just briefly mention some of the important things that I will use in my talk. like the Fefferman-Graham Expansion, the Holographic Renormalization. It's the method how to actually connect the fields in the gravity calculations to the observables in the field theory. The second part is, I would say, the main part, where I talk about numerical GR on ADS. I introduce this characteristic formulation and apply it to a very simple system, the homogeneous isotropization of an anisotropic N=4 Supergravity plasma. And in this example, I can guide you through all the necessary steps to perform these numerical GR simulations and extract the stress tensor, for instance, in its time evolution. And then I also generalize this to this boost invariant case, where it's the simplest way to introduce inhomogeneities in these kind of simulations. And in part 3, these are more advanced examples where I show you some results and discuss them for shockwave collisions, for some things that I and my collaborators did on that, for instance, calculating correlation functions, entanglement entropy. There are more exotic things like the quantum null energy condition, and if there's enough time, I talk about the steady state formation. And in the end, I give a summary. Okay, part 1, introduction. So this you already heard in Johanna's excellent lecture. So ADS-CFT is the duality between SUN n=4 supergravity theory on type 2b string theory on anti-de Sitter space. Formally, this is expressed as the following equality, where you equate the generating functional of one particle irreducible correlation functions on the CFT side to the string partition function. In this correspondence, the parameters in these two theories are related in a very specific way, such that a duality is realized. So whenever the string theory is strongly coupled, the field theory is weakly coupled, and vice versa. Johanna also told you that it's usually extremely hard to, or nowadays still impossible to perform calculations for in all parameter regimes. So we have to stick to a very specific regime, which is the so-called supergravity limit. And in the supergravity limit, you assume point-like strings. You set the length of the strings to 0, and also assume a small string coupling. And in this limit, the string theory path integral actually reduces to the path integral of classical supergravity. On the field theory side, this corresponds to the large N and large 't Hooft coupling limit. So this is very nice, because this then gives you some kind of a method to obtain observables in a strongly coupled quantum field theory by doing classical gravity calculations. So, and the observables in this quantum field theory are then obtained, the expectation values of correlation functions in the field theory are then obtained by the variation of this renormalized gravity action with respect to the boundary fields. So I will come to the point where I explain what this renormalized action is. But first, let's have a look at the holographic dictionary. So in holography, every bulk field has a corresponding operator in the boundary theory. For instance, the metric on the gravity side is dual to the stress tensor on the gauge theory side. Scalar fields are dual to scalar operators, and gauge fields are dual to global symmetry currents. Furthermore, the geometry in the bulk is in one-to-one correspondence to a state in the field theory. And if you're at finite temperature, for instance, the temperature of the field theory corresponds to the Hawking temperature of a black hole on the gravity side. In this lecture in particular, we stick to a very restricted form of the gravity action. So we only consider solutions of this following action. So it only has the gravitational field here in the Ricci tensor, and there are no extra fields like scalar fields or gauge fields now in this talk. So what we want to do next is to find an explicit relation between the gravity field, the metric, and the field theory stress tensor. For that, we first have to look at the so-called Fefferman-Graham expansion. So we expand the metric on the gravity side in the following way, where rho now is the radial coordinate of the anti-de Sitter space. And if the metric in anti-de Sitter space, or in this asymptotic anti-de Sitter space, satisfies the Einstein equation, then by the Fefferman-Graham theorem, this part of the metric has the following expansion in the radial coordinate. So these coefficients that appear in this expansion, they can now found by solving the Einstein equations order by order in the radial coordinate. And you, for instance, for this second matrix of coefficients, you find this expression, which is entirely in terms of the boundary metric, that is the leading part. So here are important remarks. For instance, these logarithmic parts that you encounter in this boundary expansion, they are related to the conformal anomaly that you get when your boundary space-time is curved and is only present when you have an even-dimensional boundary theory. And furthermore, the coefficients from dimension d on, which I mean in d equal 4, if you have a 4-dimensional boundary, means the fourth order coefficients, they cannot be extracted explicitly from this near boundary expansion. They can only be extracted from a full bulk solution. And this is mainly what we are interested in doing these numerical ADS-CFD calculations to construct the stress tensor to compute for a given source on the boundary, the response in terms of these fourth order coefficients of the metric expansion. Okay, so how do we now get this relation between the metric and the stress tensor? First, we have to put the asymptotic expansion into the action and expand it around the boundary at the fixed cutoff. This gives you an expression like that. You get some terms which are finite, and then you get a bunch of things that diverge when you send the cutoff to 0. So then to renormalize the action, we have to add appropriate counter terms to the original action such that these divergent terms are cancelled. So usually this comes with some ambiguities, and these ambiguities you have to fix by some assumptions on the correlation functions that you get then in the end, like that they at 0 temperature, for instance, vanish and so on. So then the holographically renormalized stress tensor is then obtained from varying this renormalized action with respect to the boundary metric. And then you end up with an expression like that. Okay, then when you do this program, you end up with this horrible looking expression. And this is what we will use then to compute our stress tensor. Okay. So what's then the whole idea? So let's assume the whole program that we want to follow, we want to use black hole formation as a model for thermalization or for equilibration in the field theory. So in this spirit, the relaxation and the equilibration of the black hole corresponds then to the equilibration and thermalization of the field theory state. The strategy now is to prepare a far from equilibrium state and follow its time evolution. On the gravity side, there are in principle two ways to prepare these excited states. One is that you start with a deformed or excited horizon in the bulk, and then, let's say, use fixed boundary conditions without the source and then follow the time evolution. And another way is the so-called boundary quench, where you start with a non-excited state in the bulk, and you turn on some sources in the boundary, which which then generate this excitation in the bulk, and you follow the time evolution in that way. Okay, so that's so much for the first part. Now let's come to the numerical GR part. So what I will be talking about is this characteristic formulation of general relativity. So the first thing I want to mention is that whenever we want to describe a time evolution problem in general relativity, we have to make sure that we have a well-defined initial value problem. What that means, we have to find some way how to make the equations starting from some initial condition consistent on the time evolution. So one thing that one encounters in ADS is that anti-de Sitter space is not globally hyperbolic. So it doesn't have a Cauchy slice. What that means is, okay, let me make a drawing on the blackboard. For instance, on asymptotic Minkowski spacetime, which have, let's say, a Penrose diagram that looks like that. This is globally Minkowski, globally hyperbolic. You always find a Cauchy slice. In that sense, when you provide initial data like the metric on one of these slices and the extrinsic curvature on this slice, the whole time evolution is fixed. So, because the point is, whatever happens at the boundary of the space-time cannot influence the interior of the space-time. In anti-de Sitter, this is different. You always have to provide, in addition, boundary conditions to get a well-defined initial value problem and a well-defined domain of dependence. So, for instance, if you don't provide boundary conditions, the problem is not complete. So, whatever happens at the boundary can influence what happens here in the future, and it's not sufficient to only provide the initial conditions on one of these slices. Okay, so the statement that I want to make here is if you want to make get a well-defined initial value problem, you always have to provide initial conditions and boundary conditions in ADS. This characteristic formulation is now realized in such a way that you use a light-like slicing for your space, and this can be realized by using these generalized Eddington-Finkelstein coordinates that I write here. So there is no dr squared term that's specific for this, and this form of the metric has, in addition, some residual gauge freedom. And this residual gauge freedom means that you can send the radial coordinate to the radial coordinate plus some arbitrary function of the coordinates x, and the Einstein equations are invariant under this transformation. What this allows you is that you can rescale the radial coordinate on each slice in such a way that the horizon in the bulk is fixed at a certain value, let's say 1. This is in some cases important because for one you have to exclude the singularity behind the horizon, and another reason is that, okay, what I wanted to say here is, since we're using these light-like slices, there is this phenomenon of caustics. So by the Penrose focusing theorem, matter focuses light. That means our coordinates are also focused by gravity. That means they can cross. And if these coordinates cross, our coordinate system is destroyed. So we have to avoid that. Well, and how you can avoid this is basically that you can always shift this horizon by this coordinate transformation in a region that you hide these caustics behind the horizon. And the region behind the horizon you usually exclude. Okay, now let's see how all that works for a very simple example. namely a homogeneous but highly anisotropic plasma that relaxates to its isotropic equilibrium state. This was first started by Chesla and Jaffe. This system has, on the gravity side, the following line element that realizes the symmetries also that you want on the field theory side. So physically what happens there is that you have a homogeneous system where on each point of the gauge theory you have a pressure anisotropy, which is on, let's say, in this transversal direction, has some value that is initially different from its longitudinal direction, but on each point in the space it's the same. And then if you evolve that, this relaxes to a state where the parallel pressure and the orthogonal pressure are equal. On the gravity side, this is already the solution of the gravity simulation. You start in the bulk with some anisotropy of the space-time, which is encoded in this field B here. And what happens is during the time evolution, this anisotropy travels in the space-time, and until, so what actually happens, it travels to the boundary, it's getting reflected and falls into the apparent horizon. So what you see here is the apparent horizon, the red line is the event horizon. And at late times you see both of them are equal and constant. So here in this, at this point the system is already thermalized. So let's see how to do this kind of calculations. For getting this result, you have to solve the 5-dimensional Einstein equations that I wrote here, subject to boundary conditions, where we in this case assume that the boundary metric is simple, conformal to Minkowski. To realize this characteristic formulation, we introduce this modified dotted derivative, which is a derivative along outgoing null geodesics, and this radial derivative is a derivative along ingoing null geodesics. If you use now like the metric ansatz that I showed you before, and use this notation for the derivative, something very, very important happens, namely that the originally very complicated partial differential equations, which for the Einstein equations, they decouple into a nested set of ordinary differential equations, which I write down here. So these red marked equations are constraint equations, and the blue ones are the actual evolution equations. And this is maybe the most important thing that I want to convey in my talk, is this decoupling of the Einstein equations into this nested structure. So what you see here is, here you provide some initial conditions for this anisotropy field B, and you solve for this function S, and then you can put the solution of this function S into the next equation and solve for this function S dot. So you treat these dotted derivative functions as separate variables, and you can do that step by step and get the solution only by solving ordinary differential equations. And at this step, you can express this function A, and express with A from the definition of this dot derivative this B dot, and this you can then rewrite into the time derivative of this B field. And if you have then the time derivative of this B field, you can do the time step. So important is this first equation is a constraint equation, as I already told you. It's necessary to prepare consistent initial conditions. And this fifth equation is also not needed for the time evolution. It's just used as a constraint, so you plug in the solution that you get at every step and then check how well this is satisfied. This you can use to monitor the accuracy. Okay. I'm very bad in time, so let's get a little bit faster here. So now as a next step, you want to extract from these ansatz that I wrote before the field, the variables that you need in the holographic stress tensor. For that, you make the expansion and solve the Einstein equations again, order by order in this radial coordinate. And the solution looks like that. And these functions A and B, they are now not, you cannot solve for them. These are these normalizable modes that characterize the stress tensor. The leading function coefficients, they are fixed by the boundary conditions. And as I said before, and A4, they contain the information of the field theory stress tensor. And these are then the expressions for the energy density, the pressure in the longitudinal direction, and the pressure in the transversal direction. And in this specific example, you encounter, if you do this expansion up to 5th order, that the derivative of this A4 is actually 0, which means that A4 is constant and your energy density is constant. So another step for these simulations is that you usually use this inverse radial coordinate, which brings the boundary to 0. Furthermore, you don't need to introduce a cutoff, so you can solve this problem actually numerically complete. So this you can do by factoring out the leading divergences using the known asymptotic expansions of these fields. And this you usually do in a way that you can easily read off from the redefined fields the modes that enter the stress tensor. So what we have to do now is then to solve on each of these slices these differential equations, the Einstein equations, and they take the form of a boundary value problem. So these boundary conditions and these boundary value problems, they are fixed by the near boundary expansions. And for instance, this equation 4 that I showed you in the previous page translates into this form. So the numerical problem we have is how to solve these boundary value problems, and a very efficient method to solve these boundary value problems is spectral methods. Here you expand the functions you're looking for instance, in Chebyshev polynomials. So I have to say, by assuming a certain set of basis function in which you expand, you already fix some kind of boundary conditions, which usually called behavioral boundary conditions. If you expand in periodic functions, you already implement periodic boundary conditions. So these Chebyshev polynomials, they are for non-periodic boundary conditions. What you do next is you define the spectral grid, which is you discretize in a non-equidistant way the space on which you express the function. So in this spectral Chebyshev grid, you actually express your grid in such a way that you have an equidistant partition of a semicircle, and this is projected to your to the space that you want to discretize. Then the differentiation of on this spectral grid is obtained by matrix multiplication, where the form of this matrix is given here. So I don't expect you to very understand in detail what I write here. The point is just by using this spectral method, you have this unequidistant discretization, and you transform differentiation and integration into matrix multiplication or matrix inversion. That's the point. Good, let's see how that works in practice. So this is a simple example of a boundary value problem, which has an analytic solution that I don't write down, but I plot it here. And this has boundary conditions like that. So the first step is to express the differential operator as a matrix and the right-hand side as a source vector like that. Then the solution on this spectral grid is obtained by the inversion of this differential operator matrix. So if you do that, what you find is this. So there is obviously something wrong. Can someone tell me what I did wrong here? Maybe not someone who is working with that. Maybe someone who hearing that for the first time. So no idea what I forgot to do? Okay, then I tell you. So we are, of course, want to solve a differential equation. And differential equations, they of course need boundary conditions. So what I did before was just treating this problem as a simple linear problem. I inverted the matrix and I got a trivial solution in this case. But you have to take care of the boundary conditions here as well. And there are two different ways to take care of the boundary conditions. The first one is called boundary bordering, where you replace the first line and the last line of this differential operator matrix in that way, such that if you then multiply out this line with that line, you exactly implement the first boundary condition and in the last line accordingly. Another thing is that you can use so-called basis recombination. In that way, you specify your basis function in such a way that they already explicitly satisfy the numerical boundary conditions. And if you then invert this matrix, you get, of course, the correct result. So the dots are the numerical solution. So you see this non-equidistant discretization from this Chebyshev spectral grid. And here on the right-hand side, I plot the accuracy. So since I have the analytic solution, I can compare these two. And what you see already at, like, let's say 30 grid points, I get here an accuracy of 20 digits. So if you use like 100 grid points, you get an insane accuracy of like 90 digits. Okay, so much for that. And then once you have solved these boundary value problems on these slices, you have to do the time stepping, which is then, you can in the simplest case use a simple Euler step, or more accurately, it's like this fourth order Adams-Bashforth formula, which then allows you to, these higher order methods, they usually allow you to use larger step size. But these higher methods, they of course only work at later times, once you have enough results on the first few time steps, because this method, for instance, it depends on four solutions on 4 time slices. Okay, so this is then finally the result of this analysis. So you start with some anisotropy, you do the time evolution, and this solution, it wobbles down to the equilibrium on a time scale which is order 1 of the temperature. So the red line is this constant energy in this system. So in this part, we are in the far from equilibrium regime, and at order 1 of the temperature, we are then already close to equilibrium, and the solution is then described by the quasi-normal ring down. So here are the first 2 quasi-normal modes that you get for the pressure anisotropy, for instance. So, and the nice thing is, if you can solve this problem very accurately, like here I show you this constraint that I mentioned at the beginning. So the constraint is here of order 10 to the minus 11, or even better at later times. So you can already extract by plotting this delta P as a function of time the quasi-normal modes, where the periodicity of these peaks gives you the imaginary part, and the slope here gives you the real part of the quasi-normal mode. So a slightly more complicated example is this boost invariant hydrodynamization. So there you use proper time and rapidity coordinates and assume independence of the rapidity coordinate, and plug this into this metric ansatz that we had before. Now the boundary metric looks like that, and this system then converges at late times not to a static equilibrium, but to a hydrodynamically expanding, boost invariantly expanding conformal fluid. So these leading parts are here, of course. There is this leading Birkenflow solution of hydrodynamics, and these are the viscous corrections to hydrodynamics. which are in n equal 4 Supergravity theory are given by these expressions. And if you then look at the stress tensor, you get this messy thing here. So you again start with some anisotropic situation, you let it evolve, and at later times it nicely converges to the late time hydro result, which I showed you before. These kind of evolutions, they show some universality. You can express this pressure anisotropy in terms of this clocking variable, which is given by T times the effective temperature T. And then you see that if you start with very different initial conditions for this pressure anisotropy in the beginning, after order 1 of this clock variable, all the evolution collapses to a single curve. The nice thing is you cannot only find this universality in these one-point functions in the stress tensor, but more recently we also did a study where we looked into that from the point of view of entanglement entropy, and here it's also possible to bring the entanglement entropy in a universal form and find this universal late time behavior. So let's switch now to the more advanced topics. So now there are the shockwave collisions that Ayan asked me to talk about. So in this system, you really then have to solve an effective three-dimensional gravity problem. So you have more of these metric functions you have to solve for on the gravity side, and you have a real inhomogeneous system to solve. So what happens here on this left plot, you see the time evolution of the stress tensor for this kind of simulations. You start with two Gaussian distribution of energy density and let them evolve in time. So when they crash, the energy piles up, the residuals propagate on the forward light cone, and between the plasma forms. On the right-hand side, you see an animation of these shockwave collisions. So maybe the most important finding of these kind of simulations was that the time evolution of the stress tensor follows the time evolution of hydrodynamics, of viscous hydrodynamics, already when the pressure anisotropy is very large. This is what you see here on the left plot. This is the pressure in the longitudinal direction and the pressure in the transversal direction in the central range. So it's along this line here. And what you see is that here, for instance, the dashed lines are the hydro curves. The ADS-CFD results, they're already very much on top of the hydro result, although the anisotropy is still very large, and even better in the off-central case. So these shock waves, they have also been studied for different dimensions of the shocks. So they have qualitative different behavior. So there's two qualitatively different dynamical regimes, one for wide shocks and one for narrow shocks. For these wide shocks, you find this behavior of full stopping where you crash the shocks and they almost stop each other and then they hydrodynamically explode. And the narrow shocks, they behave qualitatively differently in the sense, oh, here is the author of this paper is just entering the room, Michael Heller. In these narrow shock waves, you observe this more transparent behavior where the shock waves at first almost transparently pass through each other before only later the regime where the plasma forms is formed. And what's also special, you find behind these outgoing shocks a regime where the energy density actually can get negative. So what we have studied here, for instance, is correlations between these shocks. This you can do in holography with this so-called geodesic approximation. which give you in the limit of large conformal weight some expression for the two-point correlation function of scalar operators. What you do here is and on the right-hand side, this correlation function is described by the length of a space-like geodesic, which connects these 2 points for which you want to express the correlation function. And what you do here is you see here on the C = 0 plane the density plot of the shockwave collision of the energy density. And these are these geodesics from which you have to compute the length to express the correlation function. And you follow these shocks, you attach these geodesics, you compute these geodesics and compute their length, and you get an expression for the correlations. So this one is for the white shocks, and what you find is that initially the correlations, they grow as the shock waves approach each other, and after the collision, this is here roughly at 1, the correlations go down. This is very different in the case where you have the narrow shocks. Here you find also this initial rise, and then after the shock, the correlations, they still rise before they then decay. So you can also study, say again?
And is the contribution to these correlations from the region behind the horizon? So I guess like here in these numerical simulations, they penetrated the horizon. Did you try to track it, or it's not clear?
In this case, to be honest, I don't remember if these geodesics crossed the horizon, but I think they, at least here, I think they do. But we have not really analyzed what's the influence of crossing the horizon on this correlation function. So the point is, you see this effect, but we have not really found a handle yet to say what physical consequence it has. Yes.
So, I mean, there's a collision of nuclei, so where it's supposed to be, right? So, I mean, how can they be correlated before they collide, right? I mean.
Yeah, so that's also a good question. that's actually the correlations in the vacuum, I would say. So, and what you see is then in the outgoing shocks, you get on top of the correlations of the vacuum, the correlations that come from the interactions during the collisions. See also the vacuum correlation function has a scaling with the difference, with the distance. And this is exactly what is in this linear regime. Okay, so what it then also can do is to compute Ryo-Takanagi surfaces. Johanna introduced you to that, that you can compute the entanglement entropy from extremal surfaces in the gravity side. Here you see for the shockwave collisions case, again, the density of the collision on this plane. And here I show you cross sections of these extremal Ryo-Takanagi surface, how they reach into the bulk. And this black surface is the apparent horizon in this simulation. Here is a cross section of these surfaces, and what is interesting maybe in this case, these surfaces for the entanglement entropy, they never cross the apparent horizon. So from the surfaces and their area, you can then use for the Ryo-Takanagi formula and compute the time evolution of the entanglement entropy, and you find this also qualitatively different behavior between the wide shocks and the narrow shocks. You see first this linear grow and then a smooth fall off in a polynomial way, where for the narrow shocks you also find this steep increase in the beginning and then a characteristic shoulder, which happens only for these narrow shocks. Okay, these narrow shocks, they also have something, some very special properties. What I already mentioned before is that when you choose these shock waves narrow enough, you can, in the forward light cone, form regions where the energy density actually becomes negative. Furthermore, these shock waves these various shock waves, they can violate the so-called null energy condition. So the null energy condition is the statement that the projection of the stress tensor onto two null vectors must be positive. And here I show you a plot of a cutout of this region, and this is a narrow region, this narrow black region. In this region, the classical null energy condition is actually violated. So what I have to say here maybe is, in classical theories, classical gravity theories, this is would definitely be a problem, but in the quantum field theory, so we are in a strongly coupled field theory where we express the stress tensor, it's actually known that this classical null energy condition is violated, can be violated. So on the quantum level, the null energy condition is replaced by the so-called quantum null energy condition. So which now is expressed in terms of the entanglement entropy. So what the idea here is, I showed you this entanglement entropy calculation. You can ask, okay, so what do you need this entanglement entropy for? People have realized that these shockwave collisions, they can violate the null energy condition. There was this story then developed with this quantum null energy condition. And the idea then was to see, okay, if the null energy condition is violated, does this quantum null energy condition hold? Yeah. And this is what we did in this study. We used these narrow shockwave collisions and looked again at the projection of the energy momentum tensor and compared it to the second derivative of the entanglement entropy. So, and what you then find is you first get two different cases. So this derivative is actually a derivative along a light-like direction, and this light-like direction coincides with the light-like vector that you use for the projection. You can have two cases, that you have a deformation in one side and a deformation on the other side. And these cases, they behave actually different. Oops. These cases actually behave different. What you find is, here on this plot, I show you the left-hand side of this quantum null energy condition, which is this projection here, is the black line. And the violation of the quantum null energy condition would mean that the red-hand side is bigger than this in this black line. So these are now the derivatives of the entanglement entropy in this one direction and this other direction. And interesting, what you find that this quantum null energy condition actually can be saturated at early times by deforming in one direction, or at late times by deforming in the other direction. And more interestingly is, here you have the region where this black line goes below zero, which means that the classical null energy condition is violated. But you find that for this one deformation, the quantum null energy condition holds and is even saturated. Yeah. Yeah, so you have both cases. So in this case here, in this region where you have the deformation in this side, for the dashed line, you have both the null energy condition is satisfied because the left-hand side, so this black line is bigger than zero, and you have saturation of the quantum null energy condition because the dashed line is on top of the black line. Here, on the other hand side, you have violation of the null energy condition, which means that the black line is smaller than zero, but saturation of the quantum null energy condition because this solid blue line is on top of the black line. So, yeah, this is in the forward light cone. So this is, okay, now I understand what you mean. So this is in the central region. So this is at y equals 0. You evaluate this thing here at along this line. So you're really in the forward light cone. And this violation here, you see, this we evaluate here exactly. So you, okay, now I'm confused. No, I see. So here we are at y equals 0 and at t equals 0.5. This should be exactly the point where you have this region, you see? Okay, so are there any more questions? Okay, then let me come to my last point, which is the steady state formation. So if you bring strongly coupled quantum critical system in thermal contact, where you have two sides, one is at one temperature, one is at another temperature, this gives rise to a homogeneous steady state with a non-vanishing energy flow. So this has first been studied in 2 dimensions, and there it was found that the steady state in holography can be described by a Lorentz-boosted equilibrium state. And what happens here is that when you bring these 2 heat baths into contact, here I plot the energy density as a function of time again. If you bring these in contact, these, during the time evolution, this steady state region forms with the constant energy flow. And in 2 dimensions, the evolution is in such a way that this region broadens in a way that a shock wave with constant contour moves to the left, and a shock wave with a constant contour moves to the right. In dimensions larger than 2, this is different. What you see here is actually a shock wave moving to the colder region and a so-called rarefaction wave moving to the warmer region. The rarefaction wave is a wave that changes its shape during the time evolution. Okay, now I'm almost at the end, so let me summarize. So ADS-CFD is currently the only available tool to compute the real-time dynamics of strongly coupled theories. So I showed you this very efficient way to compute these numerical time evolutions, which is this characteristic formulation in combination with the spectral methods. I showed you how to apply this to the simplest case of a homogeneous anisotropic system that then thermalizes. Here the late time dynamics is described by quasi-normal modes. In the boost invariant case, the system does not thermalize, but it hydrodynamizes. So it evolves to a universal hydro solution. I also showed you some shockwave collisions, and there the take-home message maybe is that these wide shocks, they show viscous hydrodynamic behavior even when the pressure anisotropies are large, and that wide and narrow shocks behave qualitatively different. And also that these narrow shock waves can violate the null energy condition, but the quantum level, this null energy condition is replaced by the quantum null energy condition, and this holds. Thank you very much.
Can you go back to slide 24, I think? Yes, wonderful. So I don't know if I'm doing the math correctly here, right? But it seems like the longitudinal pressure is something like, I don't know, minus 3.5 times or so the energy density. So really you have huge negative longitudinal pressure, right? I'm wondering if there's, is there any understanding what kind of state this is in the field theory side? Because I can think of states like, this parallel plate capacitor also, right? The strongly aligned fields also, where you can get the pressure being equal to the negative of the energy density, but nothing which goes like, I don't know, 3.5 times or something like this. This just...
Okay, so in preparing this example for this plot, there was no physical consideration at all. It's just to prepare something that is far from equilibrium and then let it evolve, and by ADS-CFD to see that the isotropization or the thermalization happens at order 1 of the time. So there was no physical motivation behind choosing that large negative pressure.
But you're saying this is something that can be realized in whatever your field. In N equals 4 super Young-Mills field theory. Right?
This is the energy density in N equal 4 super Young-Mills. So these are the observables on the field.
Do you know if there is any bound on this, or can this?
There is a bound. Yeah, okay, yeah, exactly. This is maybe related to what I explained before. So you have some bound. In the quantum field theory, there are bounds on the stress tensor. But these are not given by the classical null energy condition. But nowadays, people there have found that there is this quantum null energy condition which relates, or which allows you to express bounds on the stress tensor in terms of the entanglement entropy. So there is no absolute bound that you can write down like a number. Null energy condition, you have a number, 0 on the right-hand side. The quantum null energy condition, you have also a complicated object on the other side, but it definitely gives you a bound. If this... Exactly.
So
yeah.
May I have a comment on this? So I feel like there's like additional surprising thing that is not apparent in this plot, but I'm sure Christian knows this extremely well. It turns out that like in this regime where the system is very far from equilibrium understood as pressures, it turns out that nonlinear effects might not be that important, and actually this non-equilibrium contribution comes from basically solving linearized equations. So to add to your confusion, that there is also like this effect. Regarding realizability in field theory, I think it's believed that as long as a gravitational solution does not suffer from any singularities, in a sense it's self-consistently described by gravity with two derivative gravity, then you just believe that this corresponds to some non-equilibrium state in dual quantum field theory. One problem is that there is no really an effective description. So when you're referring to longitudinal pressure being equal to minus energy density, you had in mind, say, a relation with CGC type of physics. Over here, like there's no other effective description, maybe apart from linearizing on top of equilibrium and adding the relevant amplitudes. So somehow these states seem to be fine, but well, we don't understand them microscopically. We haven't really thought about it in great detail. The reason being that this work was done around 2012-13, and the technology was not as advanced as it is now. And it was taking us like a really long time to generate like a single data point. Like a single simulation, like a single plot that Christian was displaying. I think now like these simulations are much more faster than they used to be because like there are better techniques to write them. And I think one can try to do such a simulation and try to see, for example, what happens with this negative energy density region. So one can look at the amplitude of the energy density that is negative, right, and try to see how it depends on the width of the shock. And maybe over there you would see some sort of a scaling relation. But as I said, like that requires like a lot of resolution in the parameter space, and we just didn't have it.
And one more thing to Christian, can you comment a bit on this Paul Chesler paper of this smallest drop of liquid?
To be honest, it's a long time ago when I had a look at that. So I guess you're talking about this paper where they collide these planar shocks with a localized lump of energy density, or what exactly is the paper you're talking about?
The paper that Paul Chesler wrote about this result on small systems, the flow in small systems.
Yeah, that's not my work. So I don't think that I can comment too much on that. So sorry. Maybe.
Comment about this paper. So I think like this paper really numerically demonstrates like that many of the lessons that were described or derived or learned in the context of 1+1 dimensional expansion, so either the boost invariant flow that I think appeared earlier or these shockwave collisions, pass through if you have also transversal dynamics. But in a sense, like, I mean, maybe this is something that then one should expect, because in these collisions, I think the rate of the dynamics typically in the longitudinal direction is much more violent than in the transversal direction. So like if you see high dynamization with only longitudinal features, that means that like high dynamics can be applicable like in a really widely, extreme situations for deviations from equilibrium. And when you add like transversal dynamics, this is not gonna come as something that's going to be a game changer. I mean, it's going to be a similar deviation. So you should presumably also expect in this situation that would hold in holography.
So I actually couldn't disagree more with this actually. No, I mean the reason is.
See you laughing. I added in holography.
No, I mean this is interesting to discuss perhaps, right? So no, I mean the one reason is if you look, I mean of course if you look at the 1+1 dimensional case, then I completely agree. You have insane gradients there, right? And so this is really a non-trivial question on how you somehow approach equilibrium and so forth, right? But you do have these strong symmetry constraints also, right? So clearly it's necessary to go beyond higher dimension. Now, the problem is even there, right? If you just look at somehow what is causing radial expansion early on, right? And there's some very old, I mean, relatively old work actually by Scott Pratt and Redevogt, I believe, which show that actually you can compare this in various different theories, actually also how the radial expansion works. And for instance, you see essentially no difference between ideal hydrodynamics and free streaming there. So it would actually be interesting to kind of, if at all possible, right, relax these sort of a spherical symmetry or so even further, and actually go to sort of a full 3+1D kind of setup and see how this works. Huh? But even the build-up of sort of longitudinal, sort of transverse radial flow is actually more or less universal at least at early stages, and doesn't really necessarily tell you that much about what's happening under the hood.
Well, I'm like my comment was basically that it was being observed in 1+1 dimensional setups. It was that high dynamics can be applicable when the stress tensor has deviations from perfect fluid form that are at least in 100%, like sometimes like much more, right? And now you can look at the initial stress tensor in these collisions, right? Maybe at the moment of collision or maybe soon after. And it turns out that this one, has like a similar deviations also in the longitudinal direction. But from the point of view of, like deviations from the constitutive relations, I mean, I don't see like a game changer there. I feel like one thing that occurs to me that might matter is that you might have like a very big depletion of energy density locally. So you have like a region in the transversal plane where the energy density gets like very, very low, and then like there's going to be regions where it gets very, very high. So I suspect that where the energy density gets very, very low, then you might run into some interesting effects. But I'm not sure. I mean, I'm not familiar with this work by Paul Chesler and also by Paul and Larry. Because it's like already like 4-year-old, I think, to say if they have a remark on this. But if I were to look for something that is like really interesting that's not there in the longitudinal example, that would be this. So looking at the dynamics of regions where the energy density is very low locally. And also, like, I don't think there's been like a systematic study of, like many simulations with different transversal profile, how this imprints on the dynamics. I feel like the community has not gone in this direction for some reason.